Hello and welcome to my video on Gameboy Advance sprites. In this video I will go through how to use them and what you can get from them, or rather what their limitations are. So I'll be using the Tonc library to work with the Gameboy Advance, so all terminology will be from this site here. In particular, the document you want to be kind of looking at, this one here, you can download it from the site, and all of the information I'll present here will be from chapter 7 here, or no, sorry, 7 and 8. I will only be covering the regular sprites, as they're the only ones that I use in my games and programs. So first off, what are they and why would you use them? So they're pretty much your game characters in all of the sort of main games. Anywhere you want smooth movement or smooth animation, you would use sprites, as they can move around the screen independently of the sort of background layer. So you've got 128 of them maximum that you can use. They are given their own area of memory where the sprite attributes are arranged. So your attributes are pretty much like your horizontal position, vertical position, what color palette you're using, if the sprite is set up to use 16 color tiles, or its priority, whether you want to flip it horizontally or vertically or not. So this is stored in an area of memory called Object Attribute Memory, or OAM for short, which starts at this number here in hexadecimal in the Gameboy Advance's memory range. So each sprite can have a horizontal coordinate between 0 and 511, a vertical coordinate between 0 and 255, and each sprite can be individually set to use either 16 or 256 color tiles. So I won't be going into any detail on tiles in this video, as my two previous videos pretty much cover 16 color tiles and 256 color tiles. The only thing I will explain here is with this diagram here. So you've got video RAM on the Gameboy Advance, 96 kilobytes in total, and then the sort of top area when working with tiles is split into blocks of 16 kilobytes each, so you've got a total of 6 of them, and the two bottommost are set aside for using sprites only. However, if you set the background mode to a bitmap mode, there's a chance that you will eat into the sprite graphics area, which will reduce the amount of tiles you can actually use. So you can use the sprites in any of the background modes. So coming back over here, so like I said, you can set the tiles that they use to either 16 or 256 colors, and then if you're in 16 color mode, then you can switch out a palette. One color palette has 16 colors in it, so you've got 16 color palettes to use. If you are mixing color tiles, then you have to kind of arrange your color palettes to try and not to conflict with each other, but that's obviously something for yourself. I'll quickly show you the sprites that I will be using in this demo here. These are not sprites, these are the font set here. These are two Bonsai Bill characters sprites. These will be 256 color sprites. This Rick head sprite here will be 256 colors, and the other various sprites in different sizes will be 16 color sprites. How I sort of did these was I put my two 256 color sprites at the the first sort of tiles in tile memory, as they take up twice as much RAM as 16 color tiles. Also, I arranged the color palettes, so the first block of colors would be for the Rick sprite here, and then after that the Banzai Bill sprite colors are arranged in the color memory for sprites, and then after that all of the other colors here have their own sort of palettes which are aligned to a block of 16 colors, as if sort of arranged ready for using them in 16 color mode. So the sizes of your sprites, they have to be a power of 2 in size, and they're limited to a maximum of 64 pixels in width or height. So this handy table, which I got from the ToncLib site here, shows you the available sizes that your sprite can have. Obviously bear in mind the larger the sprite, the more tiles you're actually going to use. And if you have a 256 color sprite image, then obviously that's going to take twice as much as a 16 color sprite of that same size. For example, one 16 color 8x8 tile takes 32 bytes, whereas an 8x8 tile in 256 color mode takes up 64 bytes. So there's also the size and shape to bear in mind here. So the shape, which I will explain below when I get to the attribute bits here, the shape is either set to square, tall, or wide, and then you do that with these bit flags here. So the this row here, this shape, when these bit flags are 0 here, it takes it that the sprite size will be a square, and then you have the wide rectangular shapes here, and then you have the tall shapes here. So each sprite can have its own size as well, independent from all of the others. There's also some switches to allow you to flip the image horizontally or vertically, or both at the same time. Again, independent of other sprites, and lower order sprites are drawn over the top of the higher order sprites. So the higher order sprites are drawn first. So for example, sprite 2 will be drawn below sprite 1, and sprite 0 will be the topmost sprite always. And then there's also like two sort of like modes you can kind of have. We have like a regular mode, which is a non-transformed sprite. By that I mean one which is rotated or scaled. And then you have like a fine mode, which is for like scaling, rotating. It kind of uses like a kind of like matrix which you would use for like 3D to do that. I won't be going into any details on that. Again, you can check all that out from the Coronac site here. All of the details are in there. So a regular sprite takes up 8 bytes in OAM. So one thing to note, if you're writing to OAM, then you can't write bytes. You can only send words, which are 16-bit numbers, to that area. So it takes 4 words here, which are U16 or S16, and then these are given names here. So attribute 0 is the first one in a structure, and then attribute 1, then attribute 2, and then these structures in object attribute memory are padded so that they kind of take up 8 bytes here, as you can see. And then, so this structure here is from the Tonc library, which my own code was obviously built on top of, and will also sort of hide loads of the complexities of all of this, but you will need to kind of be aware of all of this when working with these. So the attributes, basically these are all sort of split into bit flags here. So attribute 0 controls the sort of the shape that the sprite will be using. Its color mode, whether it's going to be 16 colors or 256 color tiles. Mosaic effect, again, see the Tonc docs for that, I'm not going into that. There's also special graphic effects as well. Again, I'm not interested in these. If you want to check these out, which I advise you do, then Tonc site for that. And then the sprite mode, like I was saying, you can have like a fine, normal, and then there's another thing here to hide that sprite. And then there's like a fine and double size. I'm only going to be touching the normal here. Hide sprite is also of interest. And then one thing to note here is that the sprite's Y coordinate is also stored in this attribute here as well. So that can be in the range of 0 to 255. And then attribute 1 bit flags. The top 2 bits control the sort of size along with the shape bits here. So these 2 bits and these 2 bits control the overall shape and size of the sprites. ToncLib has the attribute flags nicely named for us to use, and my own sort of sprite structure and SpriteManager will hide all of this for us. This is just here so you will know what's actually going on when we jump into the code in a bit. And then we have 2 bit flags here for flipping our sprite graphic vertically or horizontally. Thankfully, this treats the whole sort of shape as one image and doesn't individually flip individual tiles that make up the image. And then we have at the bottom bits here the sprite X coordinate, which is from 0 to 511. So notice here I've not included bit 9. That's because it's used only in the affine mode. When they're working in affine mode, some of these bits have other sort of functions, which I won't be going into here. And then attribute number 2, this is where we select a color palette for our sprite if we are in 16 color tile mode. And then there is also 2 bits here which set the sprite over background priority mode. So by default, when this is set to 0, the sprite will draw over the top of all backgrounds. If you set it to 1, then the sprite will draw over background 1, but not above background 0. And obviously it will also be above background 2 and 3. So you can have backgrounds appear above certain sprites and not others. And then we also have the tile ID in the bottom bits here. So that gives us a number here between 0 and 1023, which pretty much would allow us to sort of cover the whole sort of video RAM blocks, if you like. So when we're sort of setting our sprite up, all of these bits have to be fiddled around with to get our sprite to do anything. So that's what I'm going to cover here. We will now jump into the code. In fact, we'll run the code first, so I can show you what's going on here. So here we go. It's pretty much just a sprite parade here. What we're seeing here is some of these have the bit flags for horizontally set, and then each of them moves across the screen and then randomly appears at a different vertical coordinate once they're off the screen. Which is pretty good here. So there's only a few of them that I've used here, but you could obviously max out the whole sort of sprite range. But I will leave that as a project for yourself. So one of the first things we have to do when working with sprites is we have to enable them. So we have to set the display controller to enable sprites. So if I jump into the, I'm not going to go into the S2D module here. This was covered in the tile videos here. I'm only going to mention this bit here. So this reg display controller here, this is actually a define for a memory location in the Gameboy Advance, which, as you can see, takes an unsigned double word or a unsigned 32-bit number. Hence, normally what we do is we set the background mode flags, and then if the turn sprite on boolean is set to true, then we set our sprites to on. And then I also there's another sort of a controller for the way the graphics is aligned for sprites. I always use the object 1D type, which means that all of the sprite tiles are arranged in order of the way that I sort of put the tiles in. Check out the ToncLib document to get an understanding of the 2D way of doing things. I always use 1D. I find it works fine for all I want here. So this is all I'm going to cover in S2D here. So I will now sort of jump into the sprite module here and go over everything. So you'll see here that I've got a constant define here saying where our sprite graphics starts. So we are using the tile set number 4 in VRAM. This structure here will hold all of the key things we want from our sprite, and then all of these things here we'll put into the various attributes later on. By storing it all in a structure like this, it allows us to easily work with sprites and forget about the fiddling around with bits for each of their attributes. So one thing to note with this is I'm erasing the sprites after every sort of call to render them. this works fine for like scrolling games. The code here is basically from a game I created called Ring Dash for the Game Boy Advance. This sprite module here is pretty much the same as what I used for the game. As in, when you're drawing the characters, you only want to draw sprites which are physically on the screen, as the levels could be larger than the actual view of the screen. There's no point assigning sprites to or rather there's no point assigning the sprite structures to the hardware sprites if the hardware sprite is not on the screen. So this allows us to create loads of these sprite structures here, more than what can physically be displayed in the hardware, and then we only pass the ones we want to draw each frame to be rendered, and then the SpriteManager here will put the sprites into the object attribute memory, into the sort of hardware sprite areas, if you like. You're kind of creating like a pool, if you like. You have like there's only so many hardware sprites you can have, whereas the game might have a load of different sprites in various locations on the level. But if that part of the level is not being viewed, then you don't want those sprites to actually take up a hardware sprite allocation. That's the best explanation I can give you there of that. So all we do here is we have a T-sprite structure here. We have two creation functions here, which will return a T-sprite structure filled out for us. We just pass in the X and Y position on the screen, the tile start ID, and then the image width and height, and how many frames of animation there actually are. And then this information here will be populated by this function, and then it will return this all filled out for us. So these are almost identical functions here. We have a 256 color one and a 16 color one. Obviously in the 16 color one we need to say which palette ID we want to use with our sprite. So I haven't been playing around changing the palette IDs in this demo here, but that's something for you to play around with. So one of the first things we need to do is to call the sprite initialize function here. So I will side by side everything so we can see what's going on here. So as you can see, the SpriteManager relies on the Tonc library here, and then all of the sprite, or rather the OAM attribute stuff from the ToncLib is usually affixed with either OAM or OBJ. So OAM usually refers to the memory area, and the OBJ refers to the object, which is an individual sprite. So these are all of the functions that my SpriteManager relies upon. So now let's jump into it here. So the sprite initialize function here calls the ToncLib OAM init function, and then also notice in here as well this object attribute structure here, we create an array of sprite max here, Obviously I could have reduced the number from 128 to the amount that I'm using, but I leave this here. Something for yourself to do possibly. And then we have a private variable here to reference any individual sprite in our array. Notice these have a Z in front of them. This is like a naming convention I have to kind of make these private, if you like. Anything which has an underscore Z I consider to be like a private variable. Obviously, if you're not using an IDE, which will pick these up using IntelliSense, then you won't have to worry about any of that. And then another variable we have here is sprite last count. The reason why this is here is because we only want to draw all the sprites which have been added during any one update of our game or program. So the way that we work with these sprites is, first off, you have a T-sprite structure. You then set it up, and then all you need to do then is pass that structure to the sprite add function, and then at the end of everything, just call sprite render, and then all of the sprites which have been passed to sprite add will be put into OAM memory into an empty slot, or rather an empty space for our hardware sprite. And then this number here is obviously recorded to see how many we actually used during one frame being drawn of the game. Then sprite render first off will zero any hardware sprite numbers outside of our used count. That way we only draw what we've used, and then we can dynamically change how many we draw throughout the process of the game without having to worry about individually hiding each sprite ourselves. So we don't need to keep track of the sprite ID to hide that one sprite. This process just does all that for us. So for example, if we were to call sprite render without having any sprites added, and our sprite last count was greater than 0, then all sprites would be removed from memory and subsequently the screen. So our back to our sprite initialize here. So we basically, the OAM init function here, basically you pass an array of object attributes to it and how many sprites you intend to use, and then it then sets up the Gameboy Advance sprites for us. I also call sprite clear as well, just to make sure that all of the OAM memory is set to 0, so everything is hidden or moved off screen or whatever. And then we have 2 commands here to set the tile data. So bear in mind when you're working with 256 color sprites that each tile takes up double the amount of 16 color ones. So you will need to track that tile ID when doing that. And then this set sprite palette here expects a maximum of 16 colors, and then we pass in the palette ID, which is from 0 to 15. However, when you're working with 256 color sprites, we can use, in theory, all of the 256 colors if we like. So in this function here, we're literally set in a range of that color palette. So this is the actual color ID, and then we pass in how many colors we're actually passing in. So you would, if I do this and then I jump to the actual graphics here, you'll see here our Bonsai Bill character here takes 17 colors. It actually takes 18 colors if you include the background color. So using my Sprite graphics program, oh, not that one. Which works with the Game Boy Advance and the DS. What you would do here is, if our sprite here was the first one in VRAM and its colors were the first colors in the color palette range, as in this background here would be color 0, then we could leave it as it is when dragging and dropping it in. So for example, the size of it, we would select 256 color mode here. Its width is 64 pixels and its height is 32. Then we drag the image in. Oh, I haven't set that to take the colors from the actual image. So you'll see it says it's found 18 colors here. Now if we were to save it, it would include the first color, the sort of like the background color, if you like. Obviously we wouldn't want that if we are setting our colors here to higher in the color palette range, in which case we would need to click this option here, which will export our sprite tiles, and then it would remove whatever palette color this would be. So for example, if we wanted our sprite to start at color 18, and then we were to export this, you see it says 2 tiles. It's obviously more than that, but this takes it as this as the tile size. Now if we jump into there, so you'll see here it's got the color start at 18, and then anywhere on the image where there's the background color here, it will replace what would be color 18 with 0, and then instead the other colors will be used, and wherever this color is found it will replace that with 0. Whereas if you didn't do that, in fact I've already got that open, haven't I? So if you didn't do that, but you still wanted it to start at 18. And what this would do is this would include this background color here. Which it hasn't done. I think that's because I was okay, we'll leave that unchecked this time. And we'll set that to 18 as well. We'll get this right. Okay, let's try again. There we go. So bear in mind, if you change that setting, you might need to close the program and come into it again. So now you'll see that the first color here is color 18. And if you were to draw that sprite, it would draw that background color in place and probably wouldn't be what you would want. So that was one thing I wanted to share with you there, which can be an irritation. Okay, so that's setting up all of the colors there. And then in the add sprite function here, this is where we work with all of the attributes. So the sprite structure you pass in here. First we set our sprite pointer here to the relevant sprite in our array. So this array basically will mirror what's in OAM memory. And then we have some attribute words here that we work with to copy bits and pieces from our sprite structure. So for example here we first check to see if our width is greater than height. If it is, then we know that it's wide. So we set attribute 0 first off to the wide bit flag. And then we check which sizes our width is. So notice we don't check to see if the width is 8 pixels. Which is normally the sort of default if the bit flag is 0. So it can only ever be any of these if width is greater than height. And then we do the other there if the height is greater than width, else it must be square, and then we set attribute 0 to square, and then we set the attribute 1 sizes up there to be any of the possible size ranges there. Then we work with the tile numbers. We set up the so the frame size and tiles, that's one thing to think of as well. So this sort of stuff here, this allows us to easily animate the sprite. So the tile base would be where the first image of your character appears in VRAM, the first tile that it uses. And then the frame size in tiles is calculated in this function here, or rather not in here, in the new sprite function for us. So for example, if you had a 16 by 16 image for your sprite, then it would be 4 tiles in size, as that's 2 tiles across by 2 tiles down. And then you could easily work with your image there. So frame is which image frame you're using. So if frame was 0, it would be at the tile base. If frame was 1, then it's frame times frame size and tiles plus the tile base, which allows you to easily switch between the image frames as long as they're all stored linearly, as in one after the other, in VRAM. All this is taken care of, which is why this is calculated here. And then if this flag is set to true, then we set attribute or attribute 0 with the bit flag for 4 bits per pixel tiles. And then we also have to or the tile number with the correct tile palette. So this macro here, which is a ToncLib macro, will automatically handle working out which bit flags this palette ID corresponds to. Otherwise, if it's not 16 colors, then we would set attribute 0 to or the bit flag value for 8 bits per pixel, as in 256 color sprites. We then add the sprite's Y coordinate here, so we mask out 255 with the sprite's Y position, as that's the maximum range that sprite's Y position can have. And then we do this with 511 here for attribute 1, which holds the sprite's X position. Attribute 2 is set to the tile position. So notice here that I've not put in any of the priorities here, which would be easy enough for yourself to do. You would literally just put in a priority number in here. For example, could just have that one in there, and then you would literally just there's probably a bit flag for it as well here. Here we go. So what you would do is you would have the sprite priority, and then you would shift it by the priority shift there. And then that would, or that should do your priority. In fact, I don't think that's the, there we go. Obviously I've not changed this, so I'll need to amend these here to set that to 0. Probably shouldn't be doing this on the fly, really. There's a chance of introducing bugs doing this. So yeah, this just sets everything up for us using the sprite structure here. And then we have our two sort of flipping flags here for mirror sprite X and mirror sprite Y. These are nicely defined for us in the ToncLib to use here. So if set to true, then it ORs attribute 1 with the horizontal flip bit flag. Same for the Y one here. And then this here sets all of these attributes into the relevant sprite object for us here. So these 3 attributes are automatically set up in the structure for us. That's what this function here does. And bearing in mind that this pointer here is pointing to the current sprite ID in our sprite array. And then when we call sprite render, the sprite array is copied into OAM. We then record the last, or rather the current sprite count that we've used is then set to last, which is then used next time we call sprite render. As you can see here, it's just this bit here just zeroes out, hides the sprites that we're not using, and then these are the two functions here to set up the sprites, and that is the SpriteManager described in depth, which should make things working with them easier. But it's always nice to get an understanding of what's going on behind the scenes, so you can appreciate what it's doing more. And then, oh yeah, I'll come to the what's happening in the actual main code here. So we're only using 2 backgrounds here, background 0 and background 1. We initialize the graphics here. So I'll go into this quickly as well, as this here describes how to sort of handle working with all of these sprites. So I set up some defines here for recording which palette ID the sprites will use. Give them a meaningful name as well. You could probably put these into an enumeration possibly, although it would get messy because obviously you can only have a range between 0 and 15 when it comes to palette IDs. When it comes to the 256 color sprites, record the color start ID in the palette range, and then how many colors that sprite uses. The reason why we need to record these is it allows creating like a chain effect where we literally use these last 2 numbers to allow us to work with our next sprite. So Banzai Bill, basically the first color he's going to use will be these 2 numbers added together. And then if we were adding any other sprites after Banzai Bill, we could then use the sprite color count plus color start for the next one. However, as the other sprites are using 16 color palettes, all we're in fact doing is we're starting at the next range divisible by 16, as we're now treating that palette as being a block of 16 colors now when going into 16 color mode. And then there's also some bits and pieces here to allow creating them. Just their sizes, how many frames they have, the actual tiles, the amount of them that's constructing the images. That's all sort of stored here. And then all of the graphics and palettes are in C arrays. These are all the 16 color tiles here. Notice it's in the U32 data type. And then for our 256 color graphics, that's all in unsigned bytes. So we first set up all of the graphics here, and then we're only working with the main state title modules in this demo. Notice here we have our sprite render function in our main loop. Of course, you could move this out of there and put it wherever you want really, but for most programs it's fine just to leave it here. Just make sure that you call sprite init before using the sprites. Otherwise you could get some weird bugs popping up. And then also make sure that you set in the set mode command before these that you wish to use sprites. And then all we're doing in here is we create some T sprites to hold our characters. We have one animation timer to handle the animations for all of the sprites except Rick. So I deliberately had the initialize code here for Rick, not using the sprite new functions. So you can see me individually setting all of this up. Obviously this takes up a lot more memory doing it like this, so it made sense to create a function to do this here. So notice that in these creation functions I didn't have in the which way to set the mirror flags. Again, this could be an extra function for you to add should you wish to work with lots of mirrored tiles. Each of the initialize functions here literally just set one sprite to face in one direction, which is what we're doing here, and give them a random Y coordinate. Nothing too complicated here. Set an animation timer to 8 ticks. At the main state initialize function here, we literally just print on screen to background layer 0, initialize our sprites, and then each sprite has its own update function. Obviously it could have been better to create like a whole array of the sprites, but then that would kind of make things a bit more murkier or muddier to for you to sort of see. So I decided to split them individually so you can see what's going on here. These groups are organized by the size of the sprite itself, and then this small function here in the run function just updates all of those. And that's pretty much it. Hopefully the code will be of use to you in your own projects to allow you to quickly get up and running with sprites. So that's it for this video. In my next video I will be covering music and sound effects for the Game Boy Advance. So I shall catch you in the next one. Thanks for watching.